Hi guys, welcome back to Calculus 1 for students in international course at Kasetsart University. Today we are going to talk about continuity. It's going to be the last topic in for limits, okay, which is about continuity. So we're gonna look at a function f and see when it's continuous at a particular point. Okay, so let's start. Uh, let's first begin by looking at these examples. Which function are continuous at x equals 2? Okay, let's first look at this example. Which functions are continuous at x equals 2? So if you look at the first function here, you can see that at x equals 2, you have a white point here, which means that f2 doesn't exist, right? I'll just change this to f2, which means that f2 doesn't exist, right? Right? And you can see that from your intuition, you can just tell that the first graph is not continuous, right? So f2 doesn't exist. What is the limit when x approaches 2 from the left hand side? If x approaches 2 from the left hand side, it means that y approaches 3, right? Because if x is here, y is here, x here, y here, x here, y here, which means that when x is close to 2, y is going to be close to 3. Okay, so this is 3. And similarly, the limit from the right hand side is 3 as well. So the limit is 3. Okay, so the next graph, you can see again that it's not continuous. What is fa? Fa is f at 2. F at 2 is 3, isn't it? Because it's white here and it's black here, so it means that at 2 f is 3. Make sense? And the limit x approaches 2 from the left hand side is 3, right? Because if x is approaches from the left hand side, if x is here, y is here, x here, y is here, x here, y is here, x here, y is here, which means that as x approaches 2 from the left hand side, y approaches 3. Okay, and how about the limit from the right hand side? The limit from the right hand side, if x approaches 2 from the right hand side, you can see if x is here, y is here, x here, y is here, x here, y is here, and if x is close to 2, y is close to the 2 as well. So it means that the limit x approaches 2 doesn't exist. Okay, and for the last example, you can say that this one is continuous at x equals 2. Why? Because first you can see that f2 is actually 3, right? And the limit from the left is 3, limit from the right is 3, and the limit is actually 3. So if you just observe this example, you can see that the function f is going to be continuous if and only if f of x, which is this point, is the same as the limit, right? Otherwise it's not continuous. Okay, so in order that f continuous, we need to have that f at that point, the value of f at that point is the same as the limit. Okay, so this is the just say the concept. So Next, we're gonna look at a definition. F is defined on this interval. We say that f is continuous at x equals 2 if and only if first f2 exists. Right? You can find the value of f2. Second, limit x approaches 2 of fx exists. This means that limit x approaches 2 from the right of fx equals limit x approaches 2 from the left of fx. Make sense? And then for the last one, we need to have that f2 is equal to limit x approaches 2 of fx. Okay, so we need 3 conditions. The first condition is that f at that point needs to exist. You need to be able to find the value of f at that point. Second, the limit must exist. Okay, you need to be able to find the value of the limit at that point, which means that limit from the left and from the right are equal. And third, the value of f and the value of limit, right? The value of f and the value of limit are the same. In that case, it's going to be continuous. Make sense? Make sense? So this is the definition of, continuity. So let's look at this example. Is this continuous at x equals 2? First, we need to check that f2 exists, right? So f2 is what? Is 2 squared minus 4 divided by 2 minus 2, which is 0 divided by 0. Right? So you probably say that how about we just, factorize this into x plus 2 and x minus 2 blah blah blah. No, we won't do that, because we are going, we will manipulate, we will rearrange the terms if and only if we compute the limits. Okay, but if we are computing the value of f at 2, this is not a limit. Not limit. We actually want to find the value of f at 2. So we can't really, rearrange the term. We can't factorize, we can't, cancel things out. No, we can't do that. Okay? So guys, again, if we want to find f at 2 or f at any points, we can't factorize, we can't do anything with it. We just need to substitute x with, we just need to substitute x with 2 or, the points. And then if we get this value, it means that f2 doesn't exist. And if f2 doesn't exist, we don't need to talk about condition 2 and condition 3, because it won't be continuous. Okay, so f is not continuous at 2. Make sense? So guys, if you want to look at f2, you need to substitute x with 2, right? Just put x here as 2, x here as 2. No factorization, no, no cancel things out. No, just substitute it, compute the value. If it's divided by 0 or, some, infinity, so it means that f doesn't exist. Okay. Next, let's look at this example. First, we need to find f2. We're looking at the continuity at x equals 2. So f2, which one should we use? f it's this when f is not 2, and it's this when f is 2, right? So f2 is just 4 because we need to use this condition, right? Need to use that case when x equals to fx is. So it exists, right? It exists. Next, we need to find limit x approaches 2 of fx, right? You can look at, limit x approaches 2 from the right hand side of fx and limit x approaches 2 from the left hand side of fx, but they are going to be the same. As you can see here, this is when x is not equal to. So if you look at this case, f is also this function, right? And if you look at this case, f is also this function. It's the same function for both cases, so we don't really need to look at the left and the right limits. Okay, but if you want to look at left and right, just do so. You're just gonna get the same result. Okay, so here I have that limit x approaches 2 of fx is limit x approaches 2. Guys, x approaches 2, it means that x is not 2, it's just close to 2. Okay, so we use x squared minus 4x minus 2, and for this one we can factorize. Why? Because we are computing limits, right? We are computing limits, so we can factorize and cancel things out. So here we have that is what? 4, right? So third, we have that f2 equals limit x approaches 2 of fx. So we have 3 conditions satisfied, which means that f is continuous at 2. So this f is continuous at 2. Make sense? Okay, let's look at another example. This one. Again, the same pattern. First, we look at f2. So f2 is 4 again. Second, we need to look at limit x approaches 2 of fx. But for this one, you can see we have x equals 2. We have x less than 2 and x bigger than 2. So when x approaches 2 from the left hand side, we need to use this function. And when f approaches 2 from the right hand side, we need to use this function. Make sense? Right? So it's a bit different from the previous one, because here when x is less than 2, we have one case, and when x is bigger than 2, we have another case, right? So for this one, we need to consider limit x approaches 2 from the left hand side of fx, which is limit x approaches 2 from the left hand side of 4x plus 1, which is 4 times 2 plus 1, which is 9, right? So limit x approaches 2 from the right hand side of fx is limit x approaches 2 from the right hand side of x squared minus 4 divided by x minus 2, which is limit x approaches 2 from the right hand side of x plus 2 x minus 2 divided by x minus 2. So that's cancel out. So we have that the limit is actually 4. So guys, the limit from the left and from the right aren't equal. They aren't equal. It means that limit x approaches 2 of fx doesn't exist. So if the limit doesn't exist, we don't need to talk about the third condition anymore, right? If we don't get the second condition, we can just say that f is not continuous at 2. That's it. That's it. Okay. Then okay, for this question, which values of x makes f discontinuous? So first, guys, f is not continuous when first f of that point doesn't exist, right? So we first gonna consider this x minus 4. This is going to be 0 when x is 4, right? Right? But if x is 4, it violates this condition, because here x is always less than or equal what? Equal 3. Okay, I'm gonna look at this as well. Here I'm gonna factorize it. It's gonna be 2x and x and plus 1 and minus 3. Is it? I think so, yeah. So in this case, this is going to be 0 when x is minus half, and this is 0 when x is 3. Okay, but again, this is the case when x is greater than 3. So minus half and 3 aren't in this case. So we don't need to care about that. Okay, we don't need to care about that. And how about at 3? At 3. At x equals 3. 1. Can you find f of x? Can you find f of 3? Of course you can. It's going to be 3 squared minus 3 minus 4 divided by 3 minus 4. Right? We need to use this one because it's when x is less than or equal. Okay, we need to use this case. So it's less than or equal to 3. Okay, so here is 9 minus 7 divided by minus 1, which is minus 2. Okay, so second, limit x approaches 3 of fx. So we need to look at limit from the left and from the right, because f is defined differently when x is less than 3 and when x is greater than 3. So what we have is limit. First, I'll look at the limit from the left hand side. X approaches 3 from the left hand side of x squared minus x minus 4 divided by x minus 4. And I just substitute 3 in there, right? And it's the same as this. So I have this is minus 2. Okay? Okay? And when, to find the limit x approaches 3 from the right hand side, I need to use this. X approaches 3 from the right hand side. If you look at the real line, 3 is here. Approaches 3 from the right hand side. It means that x is greater than 3. So we need to use this function. Make sense? Make sense? So what we have here is limit x approaches 3 from the right hand side of, I'll factorize the thing up here, x minus 1 and x minus 3. Down here I have x 2x plus 1 and x minus 3. So these are cancelled out. These are cancelled out. So if we substitute x in there, what we get 3 minus 1 divided by 6 minus plus 1, which is 2 divided by 7. And as you can see, limit, the left limit is not the same as the right limit, which means that the limit doesn't exist, which means that some other colors, which means that f is not continuous at x equals 3. That's it. It's hard. Okay. Okay. Okay, let's look at another example. This one. Find value a and b which makes f continuous. Okay, so right now we want to find a and b that makes f continuous. So if f continuous, it means that f satisfies 3 condition, right? Satisfies the 3 conditions. Okay, so first, f at 1, what is it? What is f at 1? It's gonna be b plus 5, isn't it? Isn't it? Second, limit x approaches 1 of fx, it must exist, right? Right, it must exist. Okay, okay, which means that limit x approaches 1 from the right hand side. I'll look at the left hand side first, which is a plus a squared minus a minus 3, which is a squared minus 3, right? It's here, we use here, and we substitute x by, okay, let me do it a little slower. Is ax squared plus a squared x minus a minus 3, and I substitute a x with 1. So what I have is a plus a squared minus a minus 3, which is a squared minus 3. And then I look at limit x approaches 1 from the right hand side, which is 3, and square root of 2x plus 7 minus 3 divided by x minus 1. And then I multiplied, you know, the numerator and denominator by this guy. And I look at this as, you know, a minus b and a plus b. And that is the formula of a squared minus b squared, right? Right? So I have limit x approaches 1 from the right hand side of 3. A squared is 2x plus 7 minus 9 divided by x minus 1 times square root 2x plus 7 plus 3. Okay. Okay. So we have it equals to limit x approaches 1 from the right hand side of 3. X, can I do this? 2 of x minus 1 divided by x minus 1 square root of 2x plus 7 plus 3. Okay, because this guy is 2x minus 2, and then I pull 2 out, I get 2 of x minus 1. Okay, okay, and these cancel out, so I substitute x with 3 with 1. So what I have is 6 divided by square root of 9 plus 3, which is 6 divided by 3 plus 3, which is 1. Okay, okay, so guys, we have that the limit exists, so we need to have that the left limit, which is this guy, need to be the same as the right limit, which means that we have that a squared minus 3 is 1. Make sense? Because, you know, because it's continuous, so the left limit must be equal to the right limit. But the left limit is this guy. The right limit is 1. So it means that these are equal. Which means that a squared is 4. Okay? A squared is 4, which means that a is plus and minus 2. Okay, 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 okay. A is plus and minus 2. And guys, because the third condition says that this must be equal to the limit, right? Right? The third condition says that this equals to the limit, right? This equals the limit, right? But the limit is this and this, they are equal, right? Right? So I can say that the limit is actually 1. So I have that b plus 5 equals 1, which means that b is minus 4. And that's it. So the answer is a is plus or minus 2 and b is minus 4. Okay? Good? Okay. Now, we're going to look at some properties of continuity. If we have f and g, which are continuous at a, we can say that the sum of f and g is continuous. You know, f minus g is continuous. F times g is continuous. And f divided by g is also continuous if g is not 0. Okay? Okay? So the sum of continuous function is continuous. The sum, f minus g is continuous, f times g is continuous, and f divided by g is continuous when g is not 0 at a. Okay? So what can we use with that property? First, let's look at this h. Are there any value of x that fx is not continuous at? Let's say, guys, if I look at this as, fx divided by gx, when fx is x plus 1 and gx is x squared plus 9. Okay? And as you know, x plus 1 is actually a linear function, right? Which is always continuous. X squared plus y is a parabola, right? 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 Which means that it's always continuous as well. So we have that fx divided by gx is continuous if g is not 0. Okay, but what is g? G is x squared plus 9. Guys, x squared is always non-negative. So x squared plus 9 can't be 0. Right? X squared is always non-negative. Right? The smallest x squared can be is 0. So x squared plus 9 is going to be bigger than 0, right? At least 9, right? So g can't really be 0. So I can say that hx, which is x plus 1 divided by x squared plus 9, which is fx divided by gx, is continuous. Because it's f divided by g. F is continuous, g is continuous. So the division is also a continuous function. Make sense? Another theorem, it says that if you have limit of g is L and f is continuous, so limit of f of g is f of limit of g. So it might look confusing, but actually it just means that you can swap between limit and function if function is quantity. Okay. For example, this one, limit x approaches to of log this. I can tell you that this is actually the same as log of limit x approaches to of this guy. They are the same thing. Why? Because I know that the log function looks like that. That is the log, the graph of the log, which is continuous when x is positive. But right now, don't forget, we're looking at the limit x approaches to, which is positive. Okay, so log is continuous for any positive value. So if log is continuous, you can swap between the limit and the log. Basically means that you can put the log inside, put the limit inside the log, and your life is going to be much easier. Why? Because it's gonna be log of what? 2 to the power 3 minus 2 squared plus 10 plus 2, which is log of 8 minus 4 plus 10 plus 2, which is log of 16, which is log of 2 to the power of 4, which is 4 log 2. Make sense? And similarly, if you want to find limit x approaches to of cos x squared plus 2. Guys, cos is a continuous function, right? Cos is a continuous function, right? So, because you know the graph of cos, right? It looks pretty much like that. So it's continuous. So you can swap between the cos and the limit. So you have this cos, and then you have cos of 4 plus 2, which is cos 6. And that's it. It's just to say that you can swap between the continuous function and the limit. Okay, well, and that's it for continuity. Okay, and that's the end of limit chapter. So in the next chapter, we're gonna look at the derivative. Okay, it's gonna get a little bit harder, but it's gonna be more interesting. Okay, so just to sum up the whole thing, first we look at the limit by intuitive approach, right? And then we compute limits using properties, right? After that, we looked at the limit from the left and from the right, right? And then we look at the the limit at infinities, right? Limit at infinity, at minus infinity, or when limit x approaches a, it can be plus or minus infinity, right? The limits exist if the left limit equals the right limit. And then we look at the asymptotes, right? The x asymptotes and the y asymptotes, right? The horizontal and vertical. Okay, to find the horizontal, we take limit x approaches infinity and x approaches minus infinity, right? If we get L, y equals L is a vertical asymptote. And similarly, if we want to find the horizontal asymptotes, first we need to find candidates, and then we prove that x at that candidate satisfies one of the 4 conditions, right? You go back to the lecture to look at the 4 conditions. If the limit is the limit equals infinity or minus infinity, at that point A. Okay, and this is the last one, the continuity. The function is continuous when first you can find the value of the function at that point. No factorization, no being cancelled out, no nothing. Just plug in the value of x and see whether or not you can find the value of fx. Next, find the limit. Limit must exist, which means that the left limit is the same as the right limit. And third, f of x is the same as the limit, right? F of x at that point at a is the same as the limit x approaches a. And if you have three conditions satisfied, we get that f is continuous at a. Okay, and that's it for limits and continuity. Okay, so see you next time, guys. Bye bye.